So let's repeat this for the n nodes, starting with node 1 at the top. So node 1, again, is right on the boundary. We don't know the temperature of node 1, but we do know that there's a contact resistance, and we know something about the hot side temperature that on the other side of the resistance it's exposed to. So we're going to need to account for that. So let's go back. What do we for the top node or node 1, right? We're going to repeat step 2, which was do the first law. All right, we again have q dot top. All right, we've drawn here. This is q dot top. We're just generally calling it q dot top, like it's a different mechanism than the other one, but it's still there. So q dot top plus q dot bottom plus g dot is equal to 0. Right, this is for node for I equals 1. So we need to come up with terms for this again. So q dot, we'll start with q dot bottom, right? That's the easiest one. We already have an equation for that. It's exactly the same one that we had last time. So q dot bottom for node 1 is equal to T2 minus T1 times, what was it? So times K times AC over delta X. All right, some things to point out. So we now have drawn this control volume. What's the width of this control volume? Yes. So as opposed to having a control volume of delta X, as we do for nodes I, we now have a delta X over 2. But we are using for q dot bottom the conduction distance between nodes. Right? That conduction distance is still delta X for node 1. Right? You're still conducting that full length, even though the control volume is now half. All right, so that's q dot bottom. Let's see, q dot top for node 1. Q dot top for node 1 is going to be, well, we've drawn the arrow going in, so it's TH minus T1 over the resistance, which is the contact resistance. So that'd be R double prime C divided by the A, what do we call that, AC? Right. So that's my resistance, one of our resistance for top. Right. So you'll note that we're using, we're going to end up with a set of equations that includes only the n temperatures, and we should have n equations. So we have TH is defined. We're using T1 we don't know, but we have the rate equation that goes with it. And then for G dot, so G dot for node 1, that's going to be, see the resistivity rho E times delta X divided by AC I squared. But we need to account for the fact that now we only have half the volume. Right? So our generation needs to correspond to the lower value with the smaller control volume. So it's actually delta X over 2. Right? So rho E delta X over 2 AC I squared. That's for node 1. Okay. Okay, so now we have n minus 1 equations. We do the same thing again for node n. So node n, and I'll just, let's see if there's anything else interesting there. It's basically the same thing, so I'll just write it out. We have q dot top n is going to be KAC over delta X T n minus 1 minus Tn. Q dot bottom n is, we know Tc, so Tc minus Tn over R double prime C times AC. And then G dot, it's the same thing as the one above, which is rho E delta X over 2 AC I squared. Right? And it's true here as well that q dot top n plus q dot bottom n plus g dot n equals 0. Right. OK, good. So now we have n equations, n unknowns in our temperature. we should be able to take this and plug it into E's and solve it, or anywhere and solve it, right? The way we formulated this, all the T's are kind of embedded in the equation, so you'd have this implicit solution. But you can do that in E's. If you wanted to do some algebra, you could plug all this into Maple symbolically, solve for groups that multiply the different temperatures, right? Or solve explicitly for those temperatures. So there's ways to do this in any of the software that we're going to use. But for E's, it's simple. You just take this and plug it in, right? Questions? You guys have no questions today? Yeah.
So if you didn't have a contact resistance between the first node and the boundary condition, do you just enforce that the first temperature is equal to?
Yeah, that's a great point. Actually, I had written right here I should talk about that, so thank you. So what do you do if your boundary condition is not a rate? Let's say we had said here that this temperature is known at the surface to be Tc. So I don't need to go through this process then, right? I can just, my equation is just Tn equals that temperature. That's a valid equation, right? So the energy balance, I guess you could do that if you wanted to then compute, heat transfer or something like that. But if it's just a matter of solving for the unknown temperatures, you just specify the temperature directly. Okay, other questions? Yeah.
Do we need like another length term in our G dot for the length of the whole wire? It seems like the dimensions are the
So that's important because what you end up with here is just the generation for the node that you have. Right, so you should never find that in any of these equations that you're sort of accounting for the full geometry anywhere. Right? You're taking one little chunk of it at a time and writing a resistance network that relates to its immediate surroundings.
Okay.
Is that?
Aren't the dimensions of that like watts times meters though?
So this is, what is this, ohm meters, I think. So this is meters, meters squared, meters squared. This is current, which is basically a power.
So the row has the dimensions. So
This is ohm.
Sensitivity to resistance.
Yeah.
Multiplied by length over area, or just area?
Oh, it's in E's, so I'll show you in a second what the units are. But yeah, it should work out this way. But yeah, this again is G, or sorry, this is Q for N. This is G for N. Yeah. So you should always have watts for all of these terms. Like it should always come out as watts. Okay? All right. So here's our system of equations, right? We can synthesize this into a set of equations, write it succinctly. We have our three energy terms. They're equal to 0. It's because of energy balance. But you'll notice, like if I went through this and I had drawn the arrows a different way, like I had some Q dots going out or in, it actually shouldn't matter, right? You should still get this set of equations because it's just a matter of having a minus sign in front of temperatures that are flipped, right? So ultimately, you should end up with this no matter how you approach it, as long as you're careful in that process. And I'll say like right away that the challenge with numerical solutions is not that it's like conceptually difficult, it's that it's like a crap ton of bookkeeping. And it's annoying to be careful about the bookkeeping. But if you do that and you're like step by step, you go through the process, you don't jump way ahead, you try to just do it step by step, it becomes a really straightforward process.